Welcome back to my channel, friends. Today in this video what I'm going to discuss is how you can perform harmonic excitation of a single degree of freedom system using ANSYS. Even though it appears so simple, I would like to tell you that this particular example problem will drive home a lot about the methodology of performing a harmonic analysis and what are the things we should keep in mind. Start with the theory first of all. So here what I have shown is a typical single degree of freedom system wherein there is no damping. There is a mass little m and it is acted upon by an excitation force like this. We all know the governing equation of the system looks like this. I have a separate video detailing out the whole theory, but I wouldn't go to that details in this particular video. So we assume that the displacement or the response of the system is assumes something of this sort, where this capital X is again a complex number and it contains phase information. Now running the mathematical crank, what we get is capital X, which is the amplitude of the response, will look like this. So you can see here at resonance the value peaks up like this, and away from resonance the value comes down, the response comes down, and it starts with 1 when you have omega equal to 0, where omega is your excitation frequency and omega n is your natural frequency. And here also you can clearly see a shift in the phase angle. Shift in the phase angle is quite evident here as well. Now let us go to a damped single degree of freedom system. Here also things almost remains the same, but the governing equation looks different. But once we extend the same principle what we had applied for a damped system, we will get the expressions of this kind. I'm not going again into the details of the math. You can pose yourself and understand all these things. But now this is your response. This again is a complex number, but the magnitude of the complex number can be written like this. Now what about the phase? For that what we do is we multiply the complex conjugate on both sides as shown over here. Then when we look at this closely, this is a complex number. Then I would like to rewrite it like this. I'm writing capital X is amplitude of that particular quantity times minus I5 as shown over here, where 5 is tan inverse of 2 zeta omega by omega n divided by 1 minus omega square divided by omega n square. Please keep in mind that the response is lagging the input excitation. Having seen the basic theory, now we have a problem in our hand. Here I have a 1 degree of freedom system and the parameters are shown over here: the mass, the damping value, the stiffness value, and the excitation force acting at this particular point, and the excitation frequency is also given here. Now we are asked to find out the response of this particular system. So we have all the parameters. All we have to do is just plug in this formulae and we will get the amplitude of the response as well as the phase. So I'm not going into the details, but once you plug in all those things, you will get magnitude of the response as 33.26 mm, while you will get the phase as 3.81 degrees. So the response will lag the input by this amount. So these are the results what we obtain from closed form solutions. Now let's see how it compares, or how we can get the same results using ANSYS or using a commercial finite element software package also. So before we get into the nitty-gritties of the software, let me try to explain the way how we are going to idealize this model. So there will be two nodes, one node here and the second node here. there will be only one element. We are using the compin 40 element in ANSYS APDL. No need to bother too much about this technicality of this particular element and all. So this is an element which supports modeling of both a spring as well as a damper. Now, having figured out how to go about this problem, now let's go to the command stream in ANSYS APDL used to create this particular finite element model. So as we can see over here, what I'm going to define over here is that I'm telling ANSYS we are doing a harmonic response analysis, and there are multiple methods to solve a harmonic response analysis. Here I'm using the full method. Then here I'm defining this particular element. So compin 40 is the element, and I'm trying to tell ANSYS that it's an in-plane element. So the whole spring element lies in one single plane. Then I'm telling mass is only situated at one particular node, not distributed at the two nodes. Some basic things. Then in this particular line, what I'm trying to convey is the real constants, as they say in ANSYS nomenclature. Nothing, we are defining the properties for the spring elements, the stiffness, the damping value, as well as the mass. Then we are creating two nodes using these two commands. Then we are defining an element. Once we do that, the next step is we know we are exciting in the frequency range of 10 radians per second. That will be something like 1.5 or 1.6 hertz. So I'm doing an analysis where I'm varying my excitation frequency from 1 hertz to 3.5 hertz, and I'm solving this whole thing in 200 substeps. So that will be the resolution of the results I will be getting. Then KBC comma 1, what does that mean? That tells ANSYS that I'm applying the whole load in all these substeps. It's not like it gets ramped up as we move from 1 hertz to 3.5 hertz. It's there, the load is there or throughout the frequency range. Then if you remember, this was the FE model. We had the mass, then we had the spring and the damper. We are telling the node 1, this is node 1 and this is node 2. Node 1 is fixed in the Z direction, Z direction is this direction. Then the second node is acted upon by a force 100 Newton. Okay, that's what this line tells. Once, so we define the geometry, we define the loads, we define the system parameters of the system such as the stiffness and the damping. Now we are solving, then we will plot the displacement at this point at node 2. So what I'm plotting over here is the response measured at node 2 with respect to the frequency. Our interest is to find the response about this point, something like 1.6 hertz. What is the response? That's what we would like to see. And we can see a typical harmonic response here. The harmonic response peaks up at the natural frequency and it comes down. Here I'm plotting the amplitude of node 2 displacement. So this is amplitude versus frequency. While here what I have shown is corresponding to the frequency, what is the amplitude and phase. So here at 1.6 hertz, that is about 10 radians per second, I'm getting an amplitude of 33.37 mm and a phase of minus 3.84. This is closely in consensus with our closed form solutions. So with this video, what I was trying to communicate is that the basics of forced vibration response in a single degree of freedom system. So first we saw the closed form solutions. In the second part, we saw what are the options or what are the commands to be used in ANSYS APDL to carry out the same problem. We looked at certain key aspects like what are the analysis settings, how the elements are defined, and how the results are seen. So here we could clearly match both amplitude as well as of the phase corresponding to the displacement of node 2 or the mass in the actual problem. Exactly, it is exactly in consensus with our closed form solution. So this gives us a lot of confidence in using ANSYS for solving similar sort of problems. So this is how you gain confidence in solving problems which are relatively new to us. So we did a closed form, we did a simple example. We compare the results with closed form solutions. That's how we gain confidence. Thank you. Thanks for watching.